A classic scene in a factory. Someone presses a single green button, this massive machine roars to life, and then it just keeps on running, even after they've walked away. Ever wonder how that works? Well, that simple action is all thanks to one of the most fundamental ideas in automation. It's what gives the machine a memory. And today, that's what we're going to break down: PLC latching logic. All right, so here's what we're going to cover. First up, what even is latching logic? Then we'll take a quick look at where it came from. Think old school relays versus modern code. After that, we'll get into how it actually works in a PLC, see where you'd find it out in the wild, and super important, we'll finish up by talking about how to use it safely.
Okay, let's dive right into section 1. What is latching logic? Well, you can think of it as the ultimate stay-on command.
So it all boils down to this one simple but really important question. How does a machine stay on after you let go of the button? I mean, think about it. The button only sends a signal for that split second you're pushing it. So what's telling the machine to keep going? How does it remember that it's supposed to be on?
And here's your answer. Latching logic is basically a control strategy where an output, say a motor, stays energized, stays on, even after that first input signal is long gone. It literally stays latched on until a totally separate signal comes along and tells it, okay, time to turn off.
Honestly, the easiest way to wrap your head around this is to just think about a normal light switch, right? You flip it on, the light stays on. You don't have to stand there with your finger on the switch to keep the room lit. Well, latching logic is doing that exact same job, but for massive industrial machines. So, you might be thinking this is some modern computer wizardry, but not at all. Which brings us to section 2, the evolution of the latch. This whole idea has been around for a long time, way before PLCs even existed. It used to look a whole lot different. Yeah, check out this comparison. Back in the day, it was all about these physical relay circuits. They had what's called a sealing contact. You can almost picture it like a little mechanical finger that, once activated, would physically hold a circuit closed to keep the power flowing. It's clever, but it's hardware. Now look at the modern PLC logic. We do the exact same thing, but it's all done in software. No moving parts, just bits and bytes in memory, replicating that old mechanical trick.
Okay, so if it's all just software now, how do programmers actually make it happen? That's what we're getting into in section 3, the programmer's toolkit for latching inside a PLC.
When you're programming in ladder logic, there are basically two popular ways to do this. You've got your latch and unlatch instructions, sometimes you'll see them called OTL and OTU, or you've got another pair of instructions called set and reset. End of the day, they both accomplish the exact same thing. Turn something on and make sure it stays on until you specifically tell it to stop.
Let's just walk through the classic start-stop sequence step by step. Okay, so first, an operator hits the start button. Boom! The latch instruction fires and the motor gets energized. Now here's the key part. The output is now sealed in. It's latched. The operator can take their hand off the button, go for coffee, whatever. That motor is going to keep running. It stays on until and only until someone presses the stop button. That's the trigger for the unlatch instruction, which cuts the power and brings the motor to a safe stop. All right, so we've covered the what and the how. But so what? Where do you actually see this stuff? That brings us to section 4, latching out in a real world.
I mean, what's the #1 use? It's exactly what we've been talking about. Simple, super reliable start-stop control for all kinds of machinery. We're talking motors, pumps, conveyor belts, giant industrial fans, you name it. If it's in a factory and it needs to turn on and stay on, chances are there's a latch behind it.
But it's not just for on and off. It gets way more sophisticated than that. Programmers use latching to control the machine's entire state. Think of it like this. By latching different bits of memory, the PLC always knows the machine's current status. Is it running? Is it stopped? Did something go wrong and now it's in a faulted state? Or is it just sitting there idle? Keeping track of this stuff is what allows for really complex, safe, and predictable operations. It really is the machine's short-term memory. Now, giving a machine a memory, that's a powerful thing. But what happens if it remembers the wrong command? Or worse, what if it fails to forget a command when it's supposed to? The results can be, well, really bad. And that brings us to our last and, I'd argue, most important section, using latches safely.
Yeah, and I want you to really let this quote sink in for a second. Improper use of latch instructions can cause machines to continue operating when they should stop. This isn't just about writing clean code or being a good programmer. This is a fundamental safety issue. A machine that keeps going when it should have stopped is one of the most dangerous things you can have on a factory floor.
So to make sure that never happens, engineers follow a really strict set of rules. You always need a crystal clear way to unlatch the logic. And this is non-negotiable. Your safety circuits, like an e-stop button, have to be able to override any latch in the system, no exceptions. Beyond that, it's just good practice. Don't go crazy with latches everywhere because it gets confusing fast. Use comments in your code to explain what you're doing and document everything. You have to make sure the next person who looks at your code knows exactly what's going on.
So let's bring it all home with this final thought. Latching logic at its core gives a machine a memory. It lets it hold on to a command and act on it. And that puts a huge responsibility on the programmer. The big challenge, the thing every engineer has to ask themselves, is what you see right here. How do we make absolutely certain that our machines always remember the right things, and just as importantly, forget them at the right time?